Well, in this problem, we have a uniform rod whose length is 1 meter and it is kept as shown in this figure, where H is the horizontal smooth surface and W is a vertical smooth wall. That means there is no role of friction anywhere in this picture. And the rod is released from this position. We have to find its angular acceleration immediately after the release. Well, we know that when we release this rod in this position, it is going to execute a combined translation as well as rotational motion. So whenever a rigid body is in combined translational and rotational motion, it is always advisable to visualize the picture in the frame of its center of mass. So generally when you do that, it is going to make your job little easy. So before we analyze its dynamics in any frame, first of all, let us assume the values. That is the first step in all the problems of dynamics of rigid body we have done. So this is the center of mass of this rod. And when you release it, it is going to have certain acceleration. So let's say in the y direction, its acceleration is ay, and in the x direction, in the left direction, its acceleration is ax. And also that it is going to rotate. So let's say its angular acceleration is alpha. So how many unknown do you see over here? It is ax, ay, and alpha. There are total 3 unknowns. And when we are going to draw its free body diagram, the floor is going to exert a force and the wall is also going to exert a force, and therefore we are going to have 2 more unknowns. So that means basically we are going to have 5 unknowns in this problem. So we need 5 equations to solve it. So let's see how we are going to do that. Well, 2 of the equations we are going to get it from here itself. If you look at the lower end of this rod, because of the translation, it is having 2 acceleration, one in the left direction, that is ax, and one is ay in the downward direction. And because of the rotational motion, it is going to have an tangential acceleration. This acceleration, it is going to be alpha times L by 2. So if you analyze the kinematics of the bottom end of this rod, then you will realize that in the y direction, it should not have any acceleration. And therefore we can simply write that ay is equal to the component of alpha L by 2 in the vertical direction. So in order to write its component, we just need this angle, which we know that it is equal to theta. So ay becomes equal to alpha L by 2 times cos theta. So this becomes our first equation. Now similarly, if you analyze the kinematics of the upper end of this rod, then you will realize that similar to that bottom end, it is going to have acceleration due to its translation. In the left direction, it will be ax, and in the downward direction, it will be ay. And also because of the rotation which is in the clockwise direction, this upper end is going to have an acceleration in the tangential direction, which will be alpha times L by 2. So let me redraw this diagram for more clarity. For this upper end, you are going to get it as, so this is the diagram for the upper end of this rod, and if you just analyze its kinematics, we can say that its acceleration in the x direction, in the horizontal direction, must be 0 because it is constrained not to move in the horizontal direction. And therefore we can simply say that ax is equal to the component of alpha L by 2 in the horizontal direction, which can be written quite easily because this angle is going to be theta. So this angle is also going to be theta. So the component of alpha L by 2 in the horizontal direction becomes alpha L by 2 sine theta. So this becomes our second equation. Now we require 3 more equations because we have already anticipated that apart from these 3 unknowns, that is ax, ay and alpha, we are going to have 2 more unknowns, that is a normal reaction due to the floor and the wall. And therefore let's now analyze the dynamics of this rod. And as I said, when we analyze the dynamics of this rod, we are going to analyze it in the frame of center of mass, and therefore in the frame of center of mass, this rod is going to execute a pure rotational motion and the angular acceleration is alpha. So how many forces do you see in this case? Well, one of the force will be force due to gravity, which should be in the downward direction, mg. Another force will be the normal reaction due to the floor, let's say it is N1. Another force will be the normal reaction due to the wall. Let's say it is N2. And is there any other force in the center of mass frame? Well, yes, there is another force in the center of mass frame, which is a pseudo force. Why? Because the center of mass frame is an accelerated frame, and therefore we have to apply pseudo force as well. But you see, there is one thing over here, that where we are going to apply this pseudo force, we will apply pseudo force at the center of mass. And since we apply pseudo force at the center of mass, which will be mass times Ax in the right direction and mass times Ay in the upward direction, because Ax we have considered it to be in the left direction and Ay in the downward direction. Therefore, pseudo forces will be in the opposite direction of the acceleration of center of mass. And therefore, you can see that these two blue vectors are going to be the pseudo force vectors, and because of these pseudo forces, the torque about the center of mass is going to be 0. So even if we do not care about these pseudo forces, it would have been still okay. Alright, so now we are going to write the equation of torque equal to I alpha in the frame of center of mass, and not just the pseudo force. In fact, in the frame of center of mass, even this gravitational force is not going to provide any torque. So we can also remove that as well. So now you can see that the torque will be only due to N1 and N2. And the torque of N1 will be in the direction of alpha, and the torque of N2 is going to oppose it. So we have to write the equation like this, that torque due to N1 minus torque due to N2 is equal to I, which is moment of inertia about the axis of rotation passing through center of mass, which we already know that it is equal to ml square divided by 12. So the equation becomes net torque equal to ICM times alpha. Now what is the torque due to N1? Torque due to N1 is N1 multiplied by perpendicular distance from the center of mass to the line of action of force of N1. So this distance is going to be equal to L by 2 times cos of theta. So torque of N1 becomes N1 times L by 2 cos theta, it's simple geometry, minus torque due to N2 will be N2 into perpendicular distance from the center to the line of action of N2 will be this distance, which is going to be L by 2 sin theta. It's simple geometry, I'm not showing it over here. It is equal to ICM, we already know it is ml square by 12, so let us put it as ICM only times alpha. So this becomes our equation number 3. So now we need 2 more equations, because we already got 3 equations, but there are 5 unknowns. So from where we are going to get it? Well, we will analyze the translational motion in the ground frame. So if we analyze the translational motion in the ground frame, we can concentrate entire mass at the center of mass. And how many forces are acting on it? It is one of the force N1 is acting in the upward direction, N2 is acting in the left direction, and in the downward direction there is a gravitational force. And what about the acceleration of this center of mass? It is Ay in the downward direction and Ax in the left direction. So from here we are going to get 2 equations. One is writing the equation for translation in the x direction, and when you do that, it will be N2 equal to mass times Ax. This is 4th equation. And if you do it in the y direction, then you are going to get it as mg minus N1 equal to mass times Ay. This is going to be the 5th equation. So now see, in this problem there are 5 unknowns and we got 5 equations. And obviously if you solve this 5 equation, you are going to get the value of everything that you needed, but obviously this method is going to be very lengthy, so there has to be some alternative approach to this problem. So let us now talk about that alternative approach in this problem, that is by using the concept of instantaneous axis of rotation. We are going to simplify this problem in just one single step. So let's see how we are going to solve this problem by using instantaneous axis of rotation. Well, according to the concept of instantaneous axis of rotation, the combined effect of rotation plus translation of a rigid body can be considered or can be viewed as pure rotation about an axis that passes through a point of 0 velocity. And how do we find the point of that 0 velocity, which we call as instantaneous center? Well, there are various ways in which we can do that. In this problem, I'm not going to show you that. For that, you have to refer to the theory part of the instantaneous axis of rotation, in which you must have studied that if the velocity of 2 points on the rigid body is given to us, we can find the instantaneous center in this way. For example, the upper end, we know that its velocity must be in the downward direction, and for the lower end, its velocity must be in the left direction. So all we just need to do is to draw perpendicular to these velocity vectors. So when you are going to do that, you will find that the point of intersection of these two perpendicular is going to be the instantaneous center. And an axis that passes through this instantaneous center and perpendicular to the plane is going to be your instantaneous axis of rotation. And about that axis, the rod is going to perform a pure rotational motion with the same angular acceleration alpha. So as we have considered angular acceleration, so as we know that this rod is going to rotate in the clockwise direction, and therefore here also the angular acceleration will be clockwise about the instantaneous axis of rotation. Since it is a pure rotation, so we can simply write this equation, tau is equal to I times alpha. So we just have to find out the torque about the instantaneous axis of rotation. Moment of inertia will also be written about the instantaneous axis of rotation. So it becomes very easy when we try to write the torque about instantaneous axis of rotation, because the torque due to this force N2 and torque due to this force N1 about the instantaneous axis of rotation is going to be 0. And you know the reason why, because the line of action of force is actually passing through IC. So there will be torque only due to the force of gravity, which is equal to the force mg multiplied by its perpendicular distance from this IC. So this perpendicular distance is L by 2 cos theta. So the torque about instantaneous axis of rotation is mg times L by 2 cos theta, which is equal to moment of inertia about instantaneous axis of rotation. Well, we have to calculate it. So moment of inertia about IAOR will be equal to ICM plus m into r square. Basically, we are using parallel axis theorem because the axis that is passing through this center of mass of the rod and perpendicular to the plane of the screen and the instantaneous axis of rotation, they are parallel to each other. So by using this theorem, we will get the value of moment of inertia about IAOR as this ICM will be m L square by 12 plus m times. Now r should be the distance between the two parallel axes. That means the distance between IC and the center of mass. And by using cosine rule, you can get the value of this r. So how you are going to make use of this cosine rule? Well, it's quite easy. That this is your instantaneous center and this is the bottom end of the rod, and this is your center of mass, and the distance between IC and center of mass is equal to r that we have to find. And we know that this angle is 37 degree, and the distance from this lower end to center of mass is L by 2, and from the lower end to IC it is L sine theta. It's very easy. This distance is basically L sine theta. So now in this triangle we know two of the sides and the angle containing between them. We just have to find this opposite side, which we can do that by using cosine rule. So I'm not solving it over here. Assuming that you can find this value, I am leaving the value of this moment of inertia about instantaneous axis of rotation as ml square by 12 plus mr square. And so this equation mg L cos theta by 2 is equal to ml square by 12 plus mr square times alpha. So see, from here you can get the value of alpha quite quickly as compared to the previous method. But even if you do not know the concept of instantaneous axis of rotation, you can still solve this problem. However, the solution is going to be little bit lengthy. Well, whatever the method be, when you solve it, you are going to get the answer for angular acceleration as 9 radians per second square. And since it is an integer type question, the answer to this question will be equal to 9.